Okay, so welcome back. And so in the last tutorial, I showed you how to make a ggplot to visualize the difference between some machine learning model predictions. Here, scaled or unscaled inputs plugged into the one nearest neighbor's algorithm. So in this tutorial, I'm going to show you how to visualize different prediction metrics. So in binary classification, there are various different ways to quantify the prediction accuracy. So one of the easiest ones is this accuracy percent. It's just the number of labels in the test set that were predicted correctly from 0 to 100. But another really common and effective evaluation metric is called the area under the ROC curve. So a ROC curve is a plot of the true positive rate versus the false positive rate, and that is what we're going to be computing now. So how do we compute that? So first of all, I'm going to recommend that you use this one of my package called WeightedROC to compute that. So here I'm going to put that inside of an if-false statement again. Install packages WeightedROC. So let's do that. So that's on CRAN. You can install that, no problem. And so in WeightedROC, we just have a couple of functions. If you look at the help page, for WeightedROC, you either have WeightedAUC or WeightedROC. So here, this is computing a WeightedROC curve. This is computing the exact area under the ROC curve. So here, let's use WeightedROC inside of our for loop. Here, with the pred class function, we have well, actually, so we have to use a numeric value to the WeightedROC function. So here we're going to use the pred.int variable that we created earlier, which is either a 0 or 1, depending on if we're predicting a positive or a negative example, using our one nearest neighbor's algorithm. So using WeightedROC, here it doesn't have a completion, but let's look at the man page. Here in the man page, it says usage, WeightedROC, guess, label. So here, the guess should be a numeric vector of scores. Integer vector is okay too. Here, let's go, sorry, just lost the place. Here, so the first argument, the guess, would be pred int. Second argument label should be ytest. And after that, the return value is a data frame with true positive rate and false positive rate for all of the different thresholds. So let's save that as, let's call it ROC-DF because it's a data frame. So executing that line of code, it gives us this data frame with just, that's kind of a funny ROC curve. It only has 3 points on it, right? So usually when you have a machine learning model, you'll have like a more finely grained numeric score than just zeros and ones. Sometimes it'll predict the probability. Like for example, if we if we use the nearest neighbors with more than one neighbor, we will get such a probability score. And so we'll save that for a future screencast. But for now, let's just do this. Anyway, so the ROC curve looks like this. If we want to visualize this, again, we should save this data table to another list of data tables, right? So first, let's think about how to do that. Here, let's call that ROC DT list. So here I'm initializing another empty list. And what I'm going to do is I'm going to here take this ROC DF and I'm going to save that to my ROC DT list using the same index that I used for my prediction accuracy data table list. And here, again, I'm going to write a data table, and here it's going to have all of the same testful data name variables that I have over here with my prediction accuracy data table. But it's also going to have the information from the ROC-DF. So if we do that, let's see what it looks like. Well, ROC-DT list not found. Let's initialize that first. And so, yeah, so now we have our ROC-DT list at the end of this. And so here we've got a bunch of different entries for all of the different, scaled or unscaled versions of the data. and all the different test folds. Here this is for test fold 5, here this is for test fold 4, etc., right? Now if we do ROC dt gets do call rbind ROC dt list. Now we're going to end up with ROC tt, which is this this kind of data set with all of the ROC curves for all of the test folds and data sets. So if we want to visualize them, we can use another plot. So how about here we already had ggplot loaded in the last session, so let's use this time a geom path to visualize it. So usually the ROC curve is a plot of, on the x-axis the false positive rate, on the y-axis the true positive rate. And so here what I'm going to do is for every different value of data name, I'm going to use a different color. And then for every different value of, so I'm going to use also group, which is going to draw a different line for every separate value of group. So here I'm going to use paste test fold data name to get a different curve for every different value of test fold and data name. So let's execute that. Well, before executing that, well, we have to specify what is the data set that we want to use with each geom. So here, the data set here, we want to use ROC dt. So let's see what that looks like. So here, when you look at the ROC curves, you can see that, well, they're the orange lines are the 5 lines that correspond to the 5 different test folds for the scaled data model, and then the teal lines are the 5 different lines for the 5 different test folds for the unscaled model. We can see that the scaled ones are above the unscaled ones in general, so that's kind of what we expect based on our previous analysis of the accuracy rates. So we saw that you know, in the ROC curves, the best prediction is when you have a false positive rate of 0 and true positive rate of 1. So that's this corner up here. So you want your ROC curve to be as close up here as possible. So it's not quite getting there, but you can see at least the scaled ones are consistently better than the unscaled ones, so consistently higher. So that's good. So one thing that I usually do when I make these ROC plots is I usually use chord equal. So that's another ggplot2 function that's going to enforce that the x and the y-axes have the same units. So you see that here the vertical distance between 0 and 1 is the same number of pixels as between 0 and 1 horizontally here. And so that's useful for interpretation. It's also sometimes useful to add a geom AB line with slope equals 1 and intercept equals 0. And what that's going to do is, well, here I didn't add a plus. You have to add a plus after every one of these ggplot components. But here what that's going to do, that's going to emphasize this diagonal, which is kind of like the baseline uninformed classification function. And actually, you know, what we can do is we can add we can add a computation of the area under the ROC curve to our other plot. So let's think about that. So one of the evaluation metrics that people use when they're doing binary classification is the area under the ROC curve, because indeed if the ROC is going all the way up to this best point, then all the way over, then it's going to have a very high area. And so the very large numbers of the AUC, or the area under the ROC curve, are going to result in better binary classifiers. And so to do that, what we can do is we can go back inside of our for loop, and we have our ROC-df. And so our ROC-df, we can plug that into WeightedROC, WeightedAUC, and just give that ROC-df. And what does it give us? It gives us this numeric value between 0 and 1. That's the area under our ROC curve. So that's going to be for one of those iterations. So here, if we save that number as another one of the metrics, in our pred.ac dt list, we're going to be able to visualize that on our other plot. So let's do that. Yeah, and another thing that we might want to do to double check our computations is we might want to save some other evaluation metrics, like, for example, the false positive rate and the true positive rate. Let's just compute those really quickly, right? So the false positive rate, the false positive, is false positive. Well, this is going to be a vector, or a logical vector. So this is when the predicted value is 1 and the actual label in the test set is 0. That's a false positive. A false negative is when the predicted value is 0 and the actual value is 1. So to do that, we can just add those as some more evaluation metrics here. Let's try this. So how about FPR equals mean is FP. Yeah, FNR, so false negative rate, is mean is FN. And so, if we want to do the true positive rate, like we have here, is TP, that's going to be the predicted value is 1 and the actual value is 1. So then we can use true positive rate equals mean is TP. So if we execute the for loop again, we should see that now in our pred.ac dt, prediction accuracy dt, we have a bunch of other metrics now in addition to just our accuracy. Now we have the AUC, we have the false positive rate, false negative rate, and true positive rate. So, one thing that we want to do to check our calculations is we could superimpose those false positive rates on our ROC curves, and we should see it should be this kink in the ROC curve should be the false positive rate and the true positive rate that we calculated. Let's check that. So here, let's add a geom point to our ROC curve, where x is false positive rate, y is true positive rate, color is data name again. But this time data is going to be this other data set, which is pred.ac dt. So if we did our calculations right, we should see some dots lining up right here. Ooh, and they don't. So we made a mistake somewhere. What happened? That's funny. So, let's take a look at those actual numbers. That's unusual. But yeah, we'll figure it out. So, pred.ac dt. This is AUC value of yeah, there are values between 0 and 1. So I wonder if we look at just this ROC df. In ROC df, you just have the result for one of these folds. So here, let's take a look at sum is FP. Is that the same number? Yeah. Mean is FP. That's not the same number. Now, why not? Yeah, that's right, because we have to divide by something else, right? So this is the number, this is the right number of false positive, but it's not the right divisor, right? So denominator, right? So in fact, the false positive rate is not just the mean here. We have to do the sum, which is the number of false positives, divided by the number of possible, right? So the number of possible would be, in the case of the false positive rate, that's the number of y test, which are 0. In the case of the false negative rate, that's the number of y test, which are 1. And that's the sum of the y tests, which are 1, for the true positive rate as well. So let's re-execute that code, and let's figure that out. So let's see now. Now we see indeed that the dots are lining up with corresponding curves. So we have done a good job. So, yeah, the other thing that I want to do is add those numbers to the other plot. So let's take a look and try to do that. So the other plot, remember, was a plot of accuracy percent versus the data set. So what if we wanted to plot all of those accuracy metrics instead of just the accuracy percent, right? Well, first of all, pred.ac, let's take a look at what that looks like, right? Again, we've got a bunch of these different numbers, and here we have, what we'd like to do is we'd like to have every one of those maybe in different panels going from left to right. So the way to do that, the way to do that is with the data table. We can do a melt operation. So let's take pred.ac, and we're going to do melt data table melt, and here we're going to specify id vars equals these first two, test fold and data name. So all the rest of them are going to be treated as like measure variables, or variables to reshape and melt into a tall data table. So let's call this pred.ac tall, because it's going to be more rows than the previous one. So let's take a look at what that looks like. So here, what we have is a new data table where we have all of those different columns collapsed into one column called value, and a new variable, a new column called variable, which tells us what is the corresponding value, column name in the previous data table. So if we want to visualize that using ggplot2, we can use some similar code, right? And so instead of using x equals accuracy percent, here we're going to use x equals value, and now we're going to put every one of those in a different panel using facet grid. So facet grid is going to, when we give it a specification like this, it's going to mean, so on the right hand side of the tilde is the variable. So that's going to create a new, that's going to draw a column of plots for every distinct value of variable. The dot here on the left hand side means don't only draw one row. So that on the left hand side is rows, right hand side is columns, and the dot means just only one. Anyway, so let's draw that and see what it looks like. So yeah, we have to change the data set. We're using pred.ac tall now. And so what does that look like? Well, not super informative, because all of the things are on different scales, right? The percent values are between 0 and 100. These other values are between 0 and 1. So by default, ggplot2 forces all of these scales to be the same. So to get rid of that, we can use a different facet specification where we have scales equals free. And then all of the scales will be on their own scale. And so, so here we can compare the different metrics for the various different algorithms. Here we can see the accuracy percent is bigger for the scaled versus the unscaled. The AUC is bigger for the scaled versus the unscaled. False positive rate is lower. That's also better for the scaled. False negative rate is lower. That's also better for the scaled. True positive rate is better for the scaled. So yeah, so all of these accuracy metrics agree in saying that the scaled one is a little bit better consistently across all of those 5 cross-validation folds. Last thing that I wanted to mention in this one, now that we're doing it, is I usually, when I'm making these multi-panel plots, use theme BW, which turns it from this gray theme to like a black and white theme. And after that, I'm usually doing theme panel spacing equals grid unit 0 lines. And so what that does is it's just going to eliminate this spacing between the panels. So it just saves a little bit of space, which is kind of there for no reason, I think. And it's kind of, and so then you get a little a clear display. One other thing that you might want to do is you might want to edit these variables that you have, or these tick marks that you have on the x-axis. The way that you can do that is using scale x continuous breaks. So yeah, I mean, it's not super useful that, you know, one of them is like really on a different scale than the other ones. So I mean, we could go back to this and we could get rid of that, you know, 100. Where is that 100 in the code that we multiplied by? So here we computed the accuracy percent by multiplying by 100. So here we can just get rid of that, and that would probably make the plot a little bit easier to visualize. Let's see how that looks now. Right, so now we have this guy, and now the numbers are still not between 0 and 1. Maybe we didn't execute it correctly. Let's try again. You know. Yeah, so now the numbers are between 0 and 1. And yeah, I think it does probably make more sense to use you know, a more consistent scale. So here, let's do that. Scale x continuous breaks equals seek. How about between 0 and 1 in increments of 0.1? Let's see if that works. Right, so here that's a little bit better, right? So you can see that they're kind of different spacing, so that's maybe not super desirable. Right, so this one is between 0.6, the spacing between 0.6 and 0.7 is quite big here, whereas it's quite small over here. If you want to mess with that, there's another option you can give the facet grid, and that's scales equals free. And, sorry, I mean, here we already did scales equals free here. You can do space equals free, and that will give you an equal amount of spacing between the 0.6, 0.7 here and the 0.6, 0.7 over here. So yeah, so that's a visualization of the different metrics. You know, the last thing that I should probably mention in this tutorial, it's a little bit long, but it's probably worth mentioning here, is how to save the file to disk, the plot to disk. So here I'm saving the ggplot to an object called gg. Then I'm going to create a file called figure metrics.png, and then, you know, here you can give various different options. Like usually I give width equals, I don't know, how about 10, and height equals 3, units equals inches, resolution equals 100, for example. Then inside of the PNG set, we would do print GG. That says to render it on the PNG device. And after that, you know, we can take a look at that. You know, if we go to files inside of our home directory, you know, we should have something that's called figure metrics now. I think we're in the home directory. Where is that? Are we? Let's take a look. Git wd. Yeah. Well, let's just try to open it in our web browser. Open figure metrics.png. There we go. That's the figure that we just created, guys. Pretty cool. Okay, so all of that to say, thanks for listening. We just did a visualization of a bunch of different error metrics for 2 different machine learning models, and we also did a visualization of those ROC curves. So exercise for the reader, see if you can save those ROC curves to a file as well. Thanks for listening. Bye.